Okay, Assalamualaikum warahmatullahi wabarakatuh. And a very good morning. Okay, very good day to you guys. Today we will have a asynchronous lecture on the radiation thermometry and also infrared thermometry. So this is our cover picture. Okay, so I have a picture of my good friend from University Malaya, Associate Professor Dr. Najib Adib. He's doing a project on the on Sona 32, which is comparable to our infrared thermometer. Yeah? Okay, so he's been doing this project since last year during the when we have our first wave of COVID, and he managed to get a few attention from the Ministry of Higher Education, okay, and also from other ministry. Okay, I would like to acknowledge that the lecture notes, okay, it's actually from Dr. Shamehi, okay, from Sahar University of Technology. So I took his or her notes, okay, for the purpose of teaching. Okay. So for today lecture, okay, uh, we are going to cover two important topics, okay, which is really related to what we are having now, which is about the radiation thermometry and also infrared thermometry. Okay, so it is as simple as this. Okay, we know that especially for like human body, okay, animal's body, okay, and even maybe certain types of certain types of mass, okay, it has a surface temperature, okay, so it can, okay, if you understand that heat is a type of radiation, okay, so there should be a relationship between the surface temperature of an object and also its radiant power. Okay, so now uh, people have been measuring temperature, okay, using uh, uh, instrument, okay, equipment, but you have to make contact with it. Okay, so there are certain cases, okay, certain situation that you need to measure temperature contactless, okay, especially if like, okay, if you like in the industry, maybe um, you have to measure the temperature, okay, from uh, maybe because of a difficulty um, of reaching, okay, the surface, okay, of certain surface, okay, maybe it is too hot, okay, and maybe in certain application or certain situation, maybe it is too cold. So okay, so maybe so this is one of the reason. Okay, maybe in the industry, okay, they need a type of thermometer that can measure this type of situation. Okay, but for us biomedical engineers, okay, maybe um, biomedical engineers or doctors, okay, we are interested to know, okay, the temperature of a person, of a patient, okay, that have disease or type of illness that the doctors, okay, that the doctor should avoid from touching the patient. Okay, so this is where this idea will be good. Okay, if we can use a type of thermometry, okay, that works by radiation, okay, by detecting the surface radiation of our body. Okay, so medical thermography is a technique whereby the temperature distribution of the body is mapped with a sensitivity of a few tenths of a Kelvin. So this is okay. If you look at this, okay, you start. You may I'm not sure whether you are a fan of an old movie. Okay, now it becomes a classic. When I was like at your age, yeah, it is it It is a heat movie, okay, like Predator, okay, where we can sense the heat of a person and so on, okay. So yeah, then we know, okay, from our body we can radiate heat, okay, and then how to save yourself, okay, you cover yourself in mind, huh? So uh, from the graphic here, okay, which I took from the Dr. Shamiki's lecture, okay, you can see the different, okay, okay, from here we can see that maybe certain part of the body, okay, has it is reddish compared to the others, maybe because of the part, okay, have a uh, disease or something. Okay, this it is normal. Like we know that, okay, if a person have I forgot already in terms in English, visual, like wart or something. Okay, um, or even have like bruise or injuries. Okay, it would be much hotter if you compare to the other section of the body. Okay, so by understand this, okay, we know that, okay, there should be a method or system that we can detect temperature, okay, especially using the contactless method. Okay, so this is the theory behind it. Okay, um, okay, everybody that is above absolute zero. Okay, so what is it? So we go back to Kelvin, everything. I hope you still remember. Okay, on what is the minimum? What is the minimum temperature? Okay, in Kelvin and so on. Okay, okay. So above absolute zero radiates electromagnetic power. Okay, the amount being dependent on the body's temperature and physical properties. So it depends on this. Okay, it depends on this. So you have a situation, okay, which is called a black body. So what is a black body? Okay, please, okay, I know you can refer to notes in the internet and so on, but uh, to summarize all, okay, black body is a body, okay, with which is black in color. Why black? Okay, why black? Because okay, if you still remember, okay, in science, okay, whatever that you see, okay, is actually is a reflection of the color, okay, which is not absorbed. Okay, if a body absorb uh, all the light, okay, all the light, it will become black. If it reflects everything, okay, back to our eyes, okay, we have uh, white color. So a black body is an ideal thermal radiator because it absorbs everything. Okay, your this the color that you can see, okay. So you can, so this black body, okay, this black body absorb every color that we have now. Okay. So the radiation emitted from a body is given by a Planck's law, okay, multiplied by the epsilon, okay, emissivity. So you can, if you search to Google, okay, you can find a few variations of Planck's law, okay, but this is the version that we use. Okay, I made some addition here. Okay, so you need to, okay, multiply it with the emissivity. Okay, then what is C1? C1 is a constant, 3.74, okay, times 10 to the power of 4, and then C2, we have it here, okay, 1.44 times 10 to the power of 4 also. Okay, so this W lambda is at the wavelength, okay, is stated as this. Okay, so if you can, if after I uploaded the notes, okay, I made some not amendments. Okay, uh, I've added a bit, okay, because okay, the actual equation is a bit confusing. Okay, so you have this equation. So it's C2 divided by lambda T. Okay, And so T, what is T? Okay, T is a black body temperature. Okay, you need to use Kelvin, emissivity. Okay, they will give for the black body it's usually 1. Okay, if it is not a black body, so you will have another number for it. Okay, and then the Wien's displacement law gives the wavelength for which W lambda is a maximum. Okay, and also lambda m, okay, meter is inversely related to our T, is inversely related to the black body temperature. So we have this equation, this formula here. Okay, again, how is the lambda meter is inversely related to T. Okay, this is the theory. This is the theory of it. Okay. Infrared detectors and instrument systems, okay, must be designed with a high sensitivity because of the weak signals. Because as you know that the radiation coming from the body is a weak signal. Okay, it's a weak signal. So you have to design it with a high sensitivity. Yeah. Okay. And then because of nature of our body. Okay, because it's very dynamic. Okay, and then the temperature may change. If you want the accuracy of the temperature, okay, if you need the accuracy and also the precise, the temperature will be precise. Okay, you have to the thermometer that you are going to develop must have a short response time. Okay, an appropriate wavelength bandwidth requirements that match the radiation source. Okay, so that's why if you look, okay, um, before we have this COVID, okay, actually this type of thermometer maybe not that popular if you compare to even with the mercury thermometer or even the alcoholic thermometer. Okay, but because of COVID, okay, because of this COVID-19, this type of thermometer become increasingly popular. Okay, it's a boom. Okay, in the market. So last time people don't like to use it because people is it precise, is it accurate, okay, the reading is correct or not. But nowadays people have accepted, okay, as long as people say, okay, if it's 36.1, if you have a 36.5, 37, so that will be fine. Okay, but in order to produce this, okay, the suitable instrumentation must be used to amplify. First of all, as the signal is weak, okay, you need to amplify it. Then this signal need to be processed and later on display as our temperature. Okay, and then what should we have here is what are the type of sensors that we are going to use here? The radiation detectors. Okay. Most radiometers make use of beam chopper system to interrupt the radiation at the fixed rate. Okay, so we have this beam chopper system. Okay, and then we allow the use of high gain AC amplifiers without the inherent problems of stability in DC amplifiers. Okay, and the comparison of reference sources and techniques of temperature composition are more applicable to AC instrumentation. So these are the thing that is going to help the measurement of our temperature using the radiation thermometry. Okay, so there's another equation that is important, which is the Stefan-Boltzmann law. Okay, and then we go to this is how does I told you about the anatomy of the thermometer. Okay, how what are the block diagram? Okay, what are the important components that should one radiation thermometer have? Okay, you have this. Okay, you have a mirror. Okay, focuses the radiation of on the detector. Okay, so this will concentrate the radiation, the radiant energy. Okay, our heat. Okay, and then okay, we have a blackened chopper interrupts the radiation beam at a constant rate. So we have a black chopper here. Okay, black chopper blade. Okay, to interrupt the radiation beam at a constant rate. Okay. And then we have the output. We have the detector circuit. Okay. We have the detector circuit here, the IR detector. Okay. The output of the detector circuit is a series of pulses which are amplitude dependent on the strength of the radiation source. Okay. Then we have the AC signal amplifier. Okay. And then the mean value that is subject to the drift will be blocked. Okay. Then we have there's two part of it that you have to see. Okay, one is the main one here, and then there's a reference phase here. Okay, so a reference phase signal used to synchronize the phase sensitivity demodulator. Okay, so this will be synchronized. Okay, it's generated in a special circuit consisting of a light source and detector. Okay, so this part. So you can put it in three parts. Okay, the first part here about the first detection. Okay, and then the IR detector motor. Oops, sorry. Sorry for this. Okay, you have the amplifier, and then you have the phase sensitivity modulators, and then you have the filter. Okay, then you have another one, the reference phase signal. Reference phase part. Okay, for this. Okay, and then the signal. Okay, like any other type of instrument, you need to filter, and this will provide DC signal proportional to the target temperature. Okay, and then after that, after having filtered and everything, so it will display as your temperature. Yeah, so the it is easy for us, okay, to go to the restaurant anywhere, okay, just and or to the shopping store and so on, okay, and then just put your uh, just put your I forgot that yeah, then you get your temperature, okay. So but the process inside here is complicated actually. Yeah, it is not easy. Okay, okay. We go to the final part of the AC lecture, which is about the infrared thermometry. Okay, it is an instrument that determines that the internal or core body temperature of the human by measuring the magnitude of infrared radiation. Okay, it's also a type of radiation. Okay, so radiation. Okay, thermometry emitted from the tympanic membrane and surrounding ear canal. So just now is 100% contactless. So this is also a bit contactless, but yeah, you need. But this one is more accurate. Okay, we have seen it. Okay, if you have sometimes when you went to clinic and the doctors use it, they put it in your ears, okay. So and then you get the temperature. Okay, so this is the block diagram for it. Okay, so this is your waveguide. Okay, it sends your infrared, the shutter. So they have the ambient sensor, the multiplexer, analog to digital converter. Yes, the shutter switch is here, and you have your microprocessor, and then you have your digital display. Okay, so this it detects emitted energy that is proportional to the actual temperature of the subject. Okay, it has a response time in the order of 0.1 second and the accuracy of approximately 0.1 degrees Celsius, and requires a calibration target in order to maintain the higher accuracy. So compared to other maybe or mercury thermometer and so on, okay, this need a calibration. So usually a calibration, okay, after maybe a year, okay, after a few months, okay, maybe you need to calibrate it, okay, to make sure that the reading is correct, okay. So it is independent of the user technique and degree of facial activity or coefficient. So it is more reliable. It is one of the reliable technique, okay, to sense the temperature. So we can see that from our mercury thermometer, okay, then your and then for thermocouple, okay, thermistor, okay, and so on. Okay, we can see that okay, the technology is how the technology okay being used to detect temperature of a patient, okay, and also for other type of other application within the industry. So it depends on the okay how you are going to use it, okay, for what, okay, and then is this will be influenced by the cost, okay. If you want it to be more accurate, okay, more precise, maybe you can use like a thermistor, okay. If let's say you are looking at the okay much cheaper, okay, you can choose thermocouple. So these are all okay. These all should be considered, okay, when you are designing, or maybe some of you becomes a purchasing officer, okay. You are engineer, but sometimes okay maybe your department, okay, maybe your company, okay, will ask you or may ask you and advice, okay, which which type of thermometry is better for the particular particular application. Okay, thank you so much for your kind attention. Okay, so I shall see you. Um, so I shall see you uh, in the synchronous lecture. Okay, thank you very much. Assalamualaikum, and a very good day. Bye bye.